Okay, now it's working.
Okay, awesome.
Yes, perfect.
All right, next up we will have Mohamed Nagy Mustafa, who's presenting on temporal uncertainty quantification. Whenever you're ready.
So, hello everyone. So it's gonna be interesting because it's about autonomous cars. So today I will talk about perception, hallucination in perception, and how we can able to tackle it in autonomous cars. In multi-object tracking, that's the actual problem we're working on. All right, so let me just give you a quick context about what's going on. So we have sub-modules, so we have the environment, and then the autonomous car should observe what's going around, which is called perception, what's around. And after knowing this information, it started to make a decision-making based on path planning, and after that, taking the action. So the hallucination part in AI happens here in perception. And here that means if the information is coming to the decision maker is incorrect, that means the decision making is incorrect after all. And eventually the autonomous car will have a risk decision or maybe have accident. All right, so again, let me give you a quick overview about multi-object tracking. So simply from a camera sensor, so we get a frame like this one. We have an AI detection, so we detect the objects around, and then that's called localization, and then we do tracking by simply assign a unique ID for each object, and we make sure that ID is fixed or stable over time. So if you have frame at time t+1, so you have again detection, and then you need to assign the same unique IDs. All right, so actually we have two sensors, camera and lidar. Technically we are working here, and that's what's gonna happen for the rest of the presentation. So let's dive into the hallucination now. So we have a problem here, which is false positives. So when we do detections, like any detection problem we have, so usually the detector will give you false information like this one. So it's telling you there's a car here, even though there's nothing. So if to show you what's the actual problem here, let me give you an example. So say at time t, you have a false observation here, and we call it cost, and later you'll see why. So at time t+1, I have another observation. So eventually, it will end up with forming a trajectory. And this trajectory, we call it a cost trajectory, because what will happen is this trajectory will keep moving in the environment, and eventually the autonomous car will assume this an actual object moving in the environment. So so what's the problem here? So it will impact the navigation of the autonomous car, and sometimes is mismatching with an actual trajectory. So for each object in the environment, we have a trajectory, and if it's mismatched with a cost track, the one I showed to you, what happens is all information about that car I was tracking will be removed and replaced by the cost track, or the false information from AI. So how we can solve this problem? That's just more illustration. So the literature, or what we used to do is simply, we have a confidence score or detection score, and if it's high enough, we'll say that it says a true observation, and if it's low enough, we'll say it is not true. And the problem, and what we do, we just fine tune, and hopefully we're able to remove these false positives. All right, so what's the problem in that approach? So actually there are two problems here. The first problem is blocking the actual detection that we are interested in. So what happens is, if you have a detection, and this detection unlikely have a confidence less than the threshold you assigned, eventually you will lose this information. And in our case, it happens if the object is too small, or if it's overlapped with another object. All right, so what's the other problem? There's another problem, and that's more interesting, which is leaking false positives. So it doesn't matter how much time you spend to fine-tune your parameter, eventually you are not guaranteed if it's an optimal way, because it's still leaking false positive. So how we solve this problem? And that's exactly the inspiration we got from human perception. So technically we actually have the same problem, but we don't see it because our perception is continuous. It's different than how we are dealing with AI. So assume you are in a room you are not familiar with a closed eye, and you are observing an object. you have never seen before. And I told you to blink one time and tell me what you have observed. So you'll tell me, okay, in this case, you'll tell me, oh, is something red, but I'm not sure, and you blink just very quick, one time. You'll say it's something red, but I'm not sure what's it, right? So if I told you, okay, can you blink 3 more times and tell me what you have observed? You'll tell me, oh, no, now it's a red car. But if you asked me about some model, I'm not sure what's that model of that car. If I told you, okay, blink 10 more times, you'll tell me, oh, I'm certain that's a red BMW. So what happens here? So you developed information over time about what you have observed until you are certain about what you have observed is correct or not. And that's exactly what we did to formulate it algebraically. Okay, so we first collect characteristics of cosy tracks, and I'm sorry, I will go very quick at this part, and please ask me later for more details. So first, what we need something to mimic the same behavior we observed before. So it's just like a score, and this score over time increase until it tells me what you have observed is correct. So we start by introduce something called a certainty score, and this certainty score, we initially have it the confidence we are getting from the AI, but is decayed based on absent duration. And sorry, I didn't explain this part before, but absent duration is simply, okay, for false observation, so at time t, you have the observation like false bound box. At time t plus 1, you may have it, you may not. So if you don't have it at t plus 1, at t plus 2, you have it again. So the absent duration here is 1. So that's the meaning of absent duration, and that's a characteristic we collected here. So we decay the confidence we are getting from the AI by the absent duration. But this is not enough, because it will keep accumulating positive value to the certainty score. So we are adding the penalty to this part. So penalty, it's just to add some negativity in this case. So if the observation is false positive, it will keep adding a negative. So it will decrease the certainty about this observation. And eventually we have a temporal term, because here the main idea is like blinking. You keep observing and validate what you have observed. So to make it, okay. So actually this distribution, I'm sorry, I will go very quick here because of the time. So actually to make it clear here, so you can see the distribution of this equation. So we have 3 different scenarios. The first scenario, if the object is close to us, visible, we don't have any interruption in the observation. So in this case, it will have high detection score, moderate to high, and have 0 absent because it's always visible. Another case, which is small objects or far away. So in this case, what will happen is we'll have a moderate detection score, but absent duration is still okay. So still we're getting some positive in the certainty score. And so lastly, which is occluded object, when we have an overlap. So we have absent. So this car, or if I'm observing a car, so this car is not visible to me for a while, but still the object will have some or acceptable detection score. So it still will add to this certainty score, and eventually the cost objects will be at the end of the plane. So that's exactly how it represents. So with any observation, I have the current confidence, I have the last absent period, and I have the last certainty score, and it will be updated. And once it is updated, it will keep updating until it reaches to a point where I can tell this observation is valid. And to explain to you how, it's the same as blinking. So if I told you after 10 blinking, you are sure what you have observed is correct. So it doesn't matter if you blink 50 more times, because you observe the same thing. So at some point we have to stop, and that's exactly what I mean. But once the object is validated, or the observation is validated, it will just be confirmed, and we will not re-evaluate it again. So let me show you how it works in real time. So actually, at the beginning, the AI will be, I'm not sure about these objects, and once it's sure, it will be confirmed. And you can see here in the video, so this actually is the same scenario here. So you will see it's able to confirm the actual objects while removing the other ones. All right, so yeah, one more time for a video, and yeah. So at the last part here is a numerical or operational study. So simply what we did, we apply a normal, on a normal way, traditional way, to have a threshold, fine-tuned threshold, and we replace it by our proposed solution, and we make a comparison on 5 different detectors with different performance. So we have a metric called MUDA. So, or what you need to care about now, we have false negative and ground detection. Since detector is fixed, so these two terms will remain the same. So it doesn't matter if it's a traditional approach or my approach. It doesn't matter, it will remain fixed. So that means an improvement will happen in the false positive and identity switch whenever I find MUDA increased. So what we have observed, and why this makes sense, so once the detection performance decreases, the improvement increases because now the detection gives you more false positives. So the mechanism is able to remove these false positives. That's why you have high improvements like this one. So in second, you have the improvement reached to 29%. And by increasing the detection performance, the improvement will decreases because you have less false positive. So that's the end of my presentation. Thank you. You can access the paper, by the way, because there's a partial of it. And you can ask me a question here or later. Thank you.
Question for the speaker?
Thank you. That's really interesting. So my question is, might be a bit naive, but did you observe this hallucination effect when the number of objects around your detector is increasing or something? I mean, in the crowd?
Okay, so if you are talking about observing, okay, so here's the thing. The mechanism is dealing with each object individually. So you mean the running time, right? Or
I mean the number of objects around.
Yeah, because the number of objects, because this mechanism is working individually with each object because you're evaluating the observation for a certain object, right? Yeah. So it should be individual, so it shouldn't be in a group.
I see.
So yeah, so if you are talking about running time, so actually this mechanism, as you saw, it is just a small equation, like iterative equation. So it actually doesn't even like it doesn't consume any time in the running time.
All right. Thank you.
Yeah, so I guess I also have a time-related question, which is that so this mechanism becomes increasingly sure over time and eventually confirms things. I guess I was wondering like what the time scale for confirming things is. Like, do you have to worry about like running into something before you've confirmed it's there?
Yes, that's interesting. So you mean like how we test which value we need to say it's valid or not. That's what you mean?
Yeah, I guess what I'm worried about is true positives, like really confirming that something is there, but confirming it after an amount of time where it's no longer relevant for decision making.
That's actually a good question, because it's true. So this mechanism, it starts with all observation as it's not true and keeps validating until they are true. So if you observe that object and this object unlikely have a low detection score, so it will take more time to be validated. So based on our observation in the experiment, it happens when the object just appear for a little bit, like just 2-3 frames, and then it's appeared. So the other question is, do we need these objects in terms of autonomous tracking when we are tracking objects? Because most probably what happens, these kind of objects, mostly they are leaving the sensor field of view. So in this case, we don't need to track. So, but still, there's one of the limitation, by the way, because we still we need some time to validate the observation if it's correct or not. But that's totally true. Yeah. But we notice once if the object is normally if have I would say moderate to high confidence score, it will be immediately fine-tuned. And also, after all, it depends on the value you put to say that it's valid or not. As long as you decrease its value, it will be validate more objects, or less time. Will take less time to validate.
Cool, thanks.
Let's thank our speaker again.